Good morning, everybody in the lecture hall. Good morning, everybody on Zoom. So we are in another week of Big Data for Engineers, and today I will continue and finish what I explained on the big table, HBase, and so on, getting into all the physical details. But before we do so, I have questions for you. So here's the first one. It's on HDFS. Two questions, actually. With which servers must the client communicate to create a directory? First question. And the second one, to get the blocks for a file, the actual blocks, the data. So is it everything with the data nodes, or the data node for creating the directory and the name node to get the blocks, or the name node for creating the directory and the data nodes to get the block, or with the name nodes for both? That is specific to HDFS. We will see that with Colossus, that's different. Look at your answers. And we have a majority who said the name node for creating the directory. Indeed, for the metadata, it's everything with the name node, always the first point of access. And for getting the actual data, the blocks, that's from the data node, right? The name node would give the information about which blocks are in the file and which data nodes contain the blocks. But to get the actual blocks, it's the data nodes. So indeed, the majority got the correct answer. Then we have another question for you, which is, oh yes, which is better, XML or JSON? Very good. So that's exactly the what I wanted you to take away as a message for the course. It depends on the use case at hand. So in particular, when the document contains scientific papers or literature that is tagged in specific ways, then XML is the better use case. In general, XML and JSON are both trees, as we will see in the data models. And they can be made just as efficient in the processing. So it's very, very important to not let oneself be polarized towards one or the other. Also, do not do the experiment, but the best way to start a troll on an internet forum is to ask exactly that question, and then you will see all the avalanche of messages that is going to follow. The second way to get a troll on data models forums is, should I use elements or attributes to put my data? All right, so that was the other one. And finally, this one I have not explained yet. I'm going to explain today, but maybe you can actually guess. We'll discover that. I told you that HDFS has high latency. As soon as you want to write something, it takes like 1 second or something that you feel on your command line. So it's not exactly low latency. However, with HBase, we both have low latency and we're even able to write with random access, read with random access. How can it be, since HBase is stored on HDFS, right? You could think that because of HDFS, we are limited and that we necessarily would inherit the high latency. So I need to start the question. Why do you think we can still get something fast, random access, and low latency? Yes? Oh, Is it, maybe it's the volume in the room. Let me check here. So it's definitely turned on Zoom and here. Can you hear me better this way? Oh, strange. Because here I really put the audio at the maximum that I could. Still not? Oh, I will try to speak a bit louder, hoping that the people on Zoom will not. Yeah, and we will ask multimedia if maybe, because it's all locked here. I don't have access to the to these things, but we will definitely let them know that that the loudspeakers seem to have a problem. Thank you for letting me know. So let's see. Aha. So this is definitely a correct answer. And it turns out that the one that got the minimum number of answers was also correct. And we'll see that it short circuits the data nodes. Yes, don't hesitate to come up front if you want to hear me better. But I'll still try to talk louder in the lecture hall. All right. And that was it. That was what I wanted to ask. So now I'm going to go exactly to where we were. Yes, come up front. Okay. So last time, that was the last slide that I had. And we explained that there is a partitioning of the data in regions, which are intervals of rows. And these regions are assigned to the region servers that are processes that run on the same machines as the data node processes. Then we saw that if a region grows too big, because you keep writing data to the same region, then you will split it. And then it can be, so this is the split here, that one gets split. And then it can be reassigned. If then a region server has too many regions, we can just reallocate them to the other region servers, right? So this is where I left you. And what is very important is that the data is stored on HDFS. So HDFS is accessible from everywhere, all of that data. So this is why it's so simple to reassign the regions, because being assigned a region for a region server is only a responsibility. It's not the actual data. It's just the responsibility of serving the request to the clients who need data from that region. But then the data will be read from HDFS, and all of them have access to all of HDFS. For whom is that clear? Right, very good. So then let me continue over there. So I explained the HMaster. So now we'll go to the region servers and start looking deep inside all the magic that happens in there. So remember that we partition the data like a wedding cake, so the regions for the horizontal partitioning, but even within a region, we partition again vertically by column family. So it means that every partition that we have is basically the intersection of a region with a column family. So if I give you a region and a column family, that gets you a store, right? So a region plus a column family give you a store. That is the one unit by which we partition the data in. As somebody noted, the assignment to the region servers is by region. They get all the column families, all the stores for that region. So let's call them stores. It's a bit weird terminology, but yes, we need to give them some names. So let's call them stores. Now, if you look inside a store, it has multiple rows. These are all the rows that belong to the region. And it has multiple columns. These are all the columns that belong to the column family, right? Every one of these intersections of one row and one column is a cell, right? Anybody who uses spreadsheets, that should be natural, right? So the intersection of a row and a column is called a cell. And thus, a store is made of many cells. And then the idea is that all of these cells that contain the data will be stored on HDFS as files, because the only way you can store something on HDFS is as a file, because it's a file system. And the name of these files is H-file. That's the standard that specifies the file formats that these files have, right? So these are called H5. And when we have one store like this for one region and one column family, that will give us one or more H files on HDFS. And the data is persisted durably in these H files. Now, if you keep zooming in and you look at what there is in these H files, well, not surprisingly, it's a list of cells. More exactly, the way that this list of cells is going to be stored is a little bit like the battleship game, right? So let's give letters to the row IDs and digits for the columns. Of course, it's all made up. To simplify on my slides, we saw that the row IDs and the columns, these are sequences of bytes, right? Something binary. And then we just sort A1, A2, B1, B2, C1, C2, so sorted by row ID, and then for the same row ID, sorted by column. And then we store them in the H file in the lexicographic order, right? A1, then the value in there, A2, then the value in there, B1, the value, B2, the value, C1, the value, C2, the value. Who is with me? Right? And this is sorted. It is in the order of row ID and column, exactly in the order as is shown here, A1, A2, B1, B2, C1, C2. Furthermore, HBase is a versioning system. So it remembers the older versions of the data. If you write or if you update it and write new data, it will still keep the older versions. And the way it does that is that in addition to the row and the column, it also stores a version number. For example, A1 might exist in 4 versions, and then it's going to list the latest version first, let's say V4, and then V3, V2, V1, but it keeps all of them in that file. So if you look at that file, you have all of these cells with multiple versions of the same cell ordered by decreasing version. Who is with me? Right? Just want to make sure that tell the difference between completely lost or bored, right? So just make sure that you're with me, because it's quite complex. Versioning, actually, in the case of HBase, is quite straightforward. It's just a linear sequence. There's version 1, and then there's version 2, and then there's version 3, and then there's version 4, right? So it's just a line, a timeline, like with time elapsing. This is in contrast to Git. Who has been using Git or GitHub? Right? So you know that for Git, it's not linear. You can have branches, you can have all sorts of complex stuff, so it's not linear. So here, it's really as if it were a single Git branch, and then everything sequential. So that makes it easy. The way that this is achieved is by a small constraint on how people can access, meaning write to the rows. Only one person at a time can write in a row, in the same row. So if another person wants to write data to the same row, they need to wait until the first person is done. This is how you make sure that you have a linear sequence of versions, right? You take turns. Never more than one person at a time is modifying a row. Reading is fine. You can have multiple people reading the same row. But writing, you take turns, okay? All right. Now, these cells, which are listed in the H file, if we continue to zoom in, they are made of 2 things, a key and a value. In order to see that, you need to see that the battleship coordinates A1, A2, B1, B2 that identify a specific cell plus the version that uniquely identifies a value, right? If I tell you this row and that column family, that column within the column family, and this version, there is only one value that you can find, right? For that row, column, and version. So that then you have a key value model, right? The key being the row plus the column plus the version, right? So in fact, what we have in this H file is just a list of key values where each key value gives you one cell, right? Now, there's complex stuff that I'm not going to go too much into, but in addition to the key and the value, we also store the length of the key and the length of the value. It's just because the row ID or the column name is elastic. It's not a fixed number of bytes, right? It can be long, it can be short, and the same for the value. The value can be long, it can be a huge XML document of 10 megabytes, it can be a small string. And for this reason, since we have a sequence of key values, we need to know where they end. Because if I just give you the zeros and ones, and I tell you these are key values, you wouldn't be able to tell me where they start and where they stop, right? This is the reason why we also store the length of the key and the value so that we know exactly how to read them. For whom is that clear? Right, very good. And now if I zoom in a key, that shouldn't surprise you because that's something I've already told you. In the key, we have, surprise, surprise, the row ID, the column family, which is the same for all of these in the store. The column qualifier is just a fancy name for the column name. So these two identify the column, right? If I give you the column family and the column name, that's the column. Then we have the versioning, that's a timestamp. So you could consider a version like some date time, right? The point in time at which the version was created. It can be anything actually in there, but it's called the timestamp there. And then we have one more thing, I will come back to it, that is a marker as deleted. It's a way to say this one has been deleted, but that I'll come back to later. So you see, the row, the column, and the version, right, are in the key. And likewise, the gray cells here, the gray parts here is just for the length. That's again, because this is elastic, so it's just in order to know how we can parse the zeros and ones to life when we read the file. Okay, so this is it. So again, we have these sequences of key values, and this is what H files are made of. It's just a sequence of key values, and every key value gives you a cell. All right. Now, these key values, they are going to be read from HDFS, of course, and we need to be careful that we do not access single key values. The idea is that we need to group them into multiple key values to process them together. It's just to be a bit more efficient. But above all, this is going to be able to look up a key value efficiently. For this purpose, we look at the H file with zones of 64 kilobytes, roughly. And they are called blocks, but the problem with blocks is that it's already used in HDFS, so I need to give it another name. Yes?
Yes. Cedric asked on Zoom, why on slide 51 is there 2 columns in the H file representation?
Yes, so this is the key value model. It's just a different perspective to look at it. These 2 columns that you see in the H file are the battleship coordinates of the cell that you're looking at. For example, here it's really written A1, or let's say C1 here, C1. That's the coordinates here. And the value that you have in here, that might be an XML file or a JSON file or whatever is stored in there, you put here in the second column. So the second column, these are the actual values that are stored in the table, in the HBase table. And the first column has the battleship coordinates that identifies the value. So the row plus the column plus the version. Does this answer your question? Yeah, awesome, perfect. So you see the key value model is just everywhere. It's just that every time what is the key is different. But yeah, okay. So this H file, which is a very large list of key values, is going to be partitioned itself into even smaller partitions. They are called blocks, but the problem is that if we call them blocks, this is going to be confused with HDFS blocks, right? So the HDFS blocks of 128. So we cannot call them blocks without confusion. So I'm going to call them H blocks, just to disambiguate, like saying these are H blocks, H-based blocks. These are basically zones within the H file. By default, we try to size these blocks to 64 kilobytes. Now, this is not like in HDFS blocks where you exactly cut at the size of a block, 128 megabytes. Here it's elastic. It means that we will never cut a key value in the middle. we always wait until the key value stops, right? And so if there is a huge value, maybe even 10 megabytes and so on, then so be it. Then the H block is going to elastically go all the way to the end of the key value. So this is only a target, but in practice, it's rarely going to be exactly 64 kilobytes. It will wait until the last key value stops. And here's the reason why we have these H blocks. Because in order to efficiently find the key values in there, we are going to add some index structure, which you see on the left, which helps us directly locate the H block in which a key value is. For example, so we will load that into the memory of the machine. Imagine that somebody is looking for key 14. That's a battleship coordinate. Could be, for example, version 3 of cell C2, right? That's a specific key. So then we can easily look it up in this very small list of H blocks. It's just a list of H blocks with the starting and ending keys. And that tells me that this key that I'm looking for, key 14, that might be third version of C2, is in this region. And then I know that specifically this is where I need to look at, right? This is in order to accelerate the lookup of a key. And then I will find the key in the right block, okay? So what that tells us, we kept partitioning and partitioning and partitioning and just slicing things into smaller and smaller and smaller and smaller pieces. So let me do a recap of how we've partitioned these things. So we had the table that's this huge table with all the column families and rows and so on. So that's the table, which is partitioned horizontally in, what is the name for the interval of rows? Okay, say it all at the same time. Regions, yes, exactly. So yes, we slice in regions. Then we slice vertically into, what did we call them? So yes, by column family, and if you also are within a region, then that's called a store, right? So then we have the stores, which is, there's as many as column families within each region. Then one store is going to be stored on HDFS as one or more files that are called H files, yes? So now we have the H files, one or more H files. The H files are going to be partitioned into 64 kilobyte H blocks, exactly. And the H blocks contain key values, exactly. So the key, again, that's the row plus column plus version, and the value, then that's what's actually in the cell. Who is with me on that? Right? So this is how we partition things. So you see, it's a cool hierarchy of things from very large to very small. Okay. But there is a problem that you might have been wondering, because I told you in HBase, we can read and write in real time randomly. So a user could decide to insert some key in there. For example, between 13 and 14, let's call it key 13.5 or something, they could always insert something, right? So maybe there was A1, A2, A3, A4, and B1, and somebody wants to insert A5, right? So we need to insert something. But here's the problem. This list of keys here is sorted in my H file. There's a specific order. It's an ascending order, so ascending by row, ascending by column, and descending by version, but it's sorted. So we basically need to add a key value in a sorted list. But the problem is that this list is in a file on HDFS. And I told you, a file on HDFS cannot be modified. It doesn't work. You can either write it completely, you can append to it, but you cannot modify a file on HDFS. Who remembers that? Right? So we have a problem because it's on HDFS, we want to modify it, but we can't. We would have to rewrite the entire file. So that doesn't work. So there is obviously a trick in there that allows us to still be able to modify data in HBase, right? So I'm going to explain to you how it can work, that we can insert new values in spite of all the constraints of HDFS. And so now I'm going to explain what actually happens when we write new values. What the trick is. So remember this hierarchy of partitions, let's say. So we have on HDFS, I just put this nice fancy disk in there, but it's HDFS. We have all of my H files that belong to a certain store, organized in H blocks with the key values. Let's say this is the state of HBase at a certain point in time. That's the data for my store. Then comes a user. They connect to the HBase cluster, and then they ask, OK, I would like to insert this new key value, or I would like to update this cell, right? So what happens is that we don't actually directly write to HDFS. Instead, we are going to store it in the memory of the region server. Remember that the region server is a process that runs on a machine, same machine as a data node. And when the key values arrive, meaning that a user modifies data in HBase or inserted data into a table, all we do is we create a new key value in the memory and we put it in the memory. So what's happening is that, let's say a user wants to insert a new cell. There you go. We add that new key value that corresponds to the insertion of the cell. So if they inserted in row A, column 3, that didn't exist a value, then we create key A3 version 1, and then we put the value, and we store that in the memory. Let's say a user wants to update some value in the table. So let's say they want to update the value of row C column 2, which was at the latest version 3. So that's going to create a version 4. So we create a new key value with C2 version 4 with the value that the user wants to update, and we put it in memory. So you see, it doesn't matter if we create a new cell that didn't exist before, or if we update a cell, it will always result in creating a new key value, right? We just keep increasing the version. Likewise, if a user wants to delete something, then again, we create a new key value, but with this deletion marker on the right. And in the key, there will be this deleted, and that just adds a key value that says this is now deleted, right? So you might see version 1, 2, 3, 4 in the list, and then V5 will say deleted. Okay, with me? Right? So it means that whatever happens with the users interacting with HBase to modify the data, it will always result in new key values, and we just accumulate them in memory. But the problem is that at some point, the memory is going to be full, right? At some point, we will have created so many key values that the memory is going to be full. What do you think we do then? When the memory is full? Exactly, we write everything to HDFS. This is called a flush. We flush the memory, all of the key values, and we write them here to a new H file. That means that these key values that we have in the memory need to be sorted because the H file has to sort them, right? So we sort all of these key values in memory, sort them, and write them in the order of the sort, nicely divided in H blocks, right? 64 kilobytes, building also the index and so on. And then I have a new H file that contains all of the key values that just freshly come from the memory. Okay? For whom is that clear? So this is called flushing, right? The memory is full, we flush it to disk. One small optimization is that we don't actually sort in the last minute. You could think, okay, we sort once the memory is full, we sort it. What is the complexity for sorting? Complexity class, nobody knows? N log n, exactly. If n is the size, then n log n is the most efficient algorithm. So you might think, okay, that's going to take n log n. In fact, we don't wait to sort. In fact, we already, in the memory, maintain a sort. So we have some data structure. Actually, it's called a tree by computer scientists. We maintain some sort of structure in the memory that maintains the order in real time. So in fact, in the memory, it's already sorted, and we maintain the order. So whenever a key value is created, we insert it at the right place. This is where the n log n is. And when we actually write, it's O of n. It's linear, because it's already sorted, and we just flush it in linear time. Okay? Flush Remember that word, it's flushing. We flush all the key values to a new H file. That is great. I'll come to your question. That's great for HDFS because that's exactly how we want to use HDFS. We create a file in just one go. Yes? So let me repeat the question for the people on Zoom. You were basically worrying about this old H file, right? You were saying, okay, we already have these key values in there that already existed before. And so your question is, what do we do with them? Do we copy them over in some way to the new file, right? That was your question. And the answer is no. We do not even worry about this. We just take the key values that are in memory and flush them here. What happens if a user replaces some data with some new data is that we might have here old versions of some cells, let's say version 1 and 2 of C3. And here we might have version 3 and 4 of the same location, right? All we did is add new key values because we just create new versions. So we don't need to worry about the old versions. And I'll show you later that it's when we read the data, we will read from here, from everywhere. And then upon reading, you notice, okay, these are versions 1 and 2, these are version 3 and 4. So I just take version 4 and I ignore version 1 and 2 and 3. They are there, but I'm just going to ignore them, right? Does it answer your question? Awesome. So we don't worry about the old files. We keep them. They're there. This is old data. And the new data, possibly newer versions, just gets flushed in a brand new H file. Any other questions? Yes?
Yes, Cedric on Zoom asked, what if the memory size is much smaller than the total file? That is, there are many more rows and columns than what can be stored in one H file. Maybe maybe then it means the memory store is much smaller than the total file or larger. I'm not sure.
Mm-hmm. So let me answer by saying it's the other way around. As soon as the memory is full, we flush. And of course, in the memory, we don't care how many were accumulated, right? It's not, of course, it's very unlikely that what is going to be in the memory is going to cover all rows or all columns. It's very unlikely. We just accumulate things in memory and then we flush when the memory is full, right? So what is in the memory is going to be comparatively small compared to the entire store, right? And then another element of answer to your question is that if at some point there's so much data in the same region, then we just split it. So the split is what I explained last week, that if a region is too big, we just split it into 2 regions, and that's it. Does it answer the question? Yeah. So what is determining here is when the memory is full, we flush. Right? That's a very, very simple rule. But now we still have a problem. The problem is, what if there is a fire or whatever and the data center burns down? That was in the memory, right? Before I flushed. That's in the memory. So if at that point, if there is a catastrophe or an electricity a shortage or whatever and all the computers crash, we have lost the data that is in the memory. Who agrees? Right? Because that doesn't survive when the electricity goes away. Only the H files we would have. So that means that all of this fresh data that was recently added, we would lose. So there is a little bit of a precaution that we need to take in addition to that, is that before we add a new key value to the memory, we are going to also store it somewhere else in a log that we call an H log. So as soon as the user wants to modify something, we first put in the log, this is the modification, and after it's been put in the log, then we put it in the memory. That log here is stored on HDFS2. So this goes to HDFS. So everything that is in there, it's going to be persisted, it's going to survive an electricity shortage or a fire or whatever. But now you might wonder, we just moved the problem to something else because that's going to take time to write to the H log, right? But in fact, no, because the H log is sorted by time. It's not sorted by key, it's sorted by time. So whenever you put something to the H log, it's always appending. You always put it at the end of the log, always at the end. And appending in HDFS is no problem at all. So we keep appending, just a journal of all the modifications. And then after that, we put it in the memory. And then the memory is going to be flushed in the H file. So now it means that, I just finish that and then come to the question, if there is a fire or the computer's crash or whatever, we just take the H log and replay it to get back the key values. Yes?
Yes, there's a follow-up question of you answering the question in the room that in that case, data modification may not be grouped by region anymore, or?
Oh, yes, they are always grouped. So basically, when a user interacts with HBase, whatever they modify, you look at the region that they're modifying, and then it's going to specifically go to the memory of the region server in charge of the region. If a user modifies multiple regions, then it's going to go to the mem store, so to the memory of all of these region servers. Right. So it's always like the user modifies something. We ask in what region is that, what they modify, and for all of the regions that are affected by what the user is doing, we put key values in the memory of the region servers that are in charge of the regions that the user is touching. Does it make sense? Okay. Maybe I'll add a precision. The user will have to connect to the region servers for which it wants to modify the regions. Right? So the user is going to ask for the HMaster, and then it will connect to the region servers.
Yeah, so Cedric said, but I thought the previous data was not touched, so how do we reach the regions?
Oh, so indeed, you do not touch the old data. You do not. So let me maybe explain it with logical and physical. Logically, in the data model, you modify the data, right? There might have been some data at a specific place, and then you want to replace it by some new data. But that is the logical level. That is when the user interacts with HBase, and it feels like they are modifying the data, right? So this is feeling. If they want to modify the data in some place, then the client is going to connect to the region server in charge for that region for which they want to modify the data. But then what happens physically with this region server is not that they're modifying anything. Instead, what the region server will do is create a new key value with a new version number with the new data that needs to be replacing the old data. And that's always done by adding new key values in the memory, right? And so it's just going to have a higher version number, just like you do in Git. When you want to modify files in Git, that only adds a new revision, right? It doesn't actually modify the data. It only adds a new revision at the end of your branch that has the diff. Does it make sense?
So data from mem store is flushed to the correct region server, basically.
The mem store here, so let me go back here, right here. This is the region server. So the memory here of the mem store is the region server that is responsible for that region. And every region server is going to have a memory like this. And every region server will keep in its memory all the new key values that correspond to the regions that it's handling, right? And then when it's flushed, that goes to HDFS, right? Now, if you remember what I told you about HDFS, the region server would basically act as a client of HDFS. And we saw that when you write a file to HDFS, the first replica of every block will be where? On the same machine as the client. And remember that the region server is on a machine where there is also a data node on the same machine. So that data, the H file, the first replica will land on the same machine, right? Physically, because of HDFS. But that is only to do with HDFS. Right? So again, I repeat, this is the memory of the region server process that contains all of the fresh key value pairs. And the region server flushes, writes to HDFS this file, this H file, and that goes to HDFS. And because there's a data node on the same machine, all of that, one copy of that, will land on the physical hard drive on the same machine that is both running the region server and the data node. Who is with me? Right? It's a big puzzle that we're assembling, but you see everything is falling into place, like things that I've told you even 2 weeks ago. Now it's just nicely assembling into a puzzle, and just needs time to digest, right? But it's all connected. It's all good? Question? All right. Of course, I will continue to explain the details of that. So now we've protected ourselves against loss of data, right? Just in case the region server is out of service and we lose that data, we took the precaution of writing it to an HLog, which is an HDFS file, sorted by time, which is just a journal, and then we put it in the memory. All right. And so we are going to flush whenever the memory is full. So if you want to be more precise, is when a specific mem store is full. Mem store is just the name for the memory of the region server. Or you can also monitor the total memory over the entire cluster. You add the size of all the key value pairs across the entire cluster, and then you can also have some thresholds that says if there's more than, just saying at random, 100 gigabytes of key values over my entire cluster on all the region servers, then I flush everything. That could also be a strategy that I have. And I could also have a condition based on the log. I could also say when the H log is full or has a certain size, I can also trigger a flush, right? So these are the possible things. Now I have an animation for something I already explained, but I'm going to make sure to explain it again. When we read something, a user wants to connect to HBase and read the data that is in there. Yes?
Yes, there was a question from Manuel that got overlooked. So when you talk about memory, do you mean the one of the device we are using, or is it some sort of cache related to HBase?
That is not a cache. This is really the working memory, the RAM of the machine on which the region server is running, right? It's really the RAM, the same you have on your laptop, the working memory, right? This is not a cache. I'll come to the caches later. This is not a cache because it's fresh data that doesn't exist on disk. So it's not a cache. It's really just the memory, the working memory, the RAM of the region server, right? Awesome. So now that we've had users interact with HBase and they modified stuff and edited data and deleted data and replaced data and created new data, we've accumulated a few H files. Each of one comes from a previous flush. So here we flushed twice for that region. Plus we have even more key values in memory for more recent changes. And now another user comes and say, okay, I would like to read the data in that region. Please give me the data for that region. Where do you think we should look to serve that user? Should we look in the memory? Should we look at the most recent H file? Should we look at the older ones? Where do you think we should look? In memory first? Any other ideas? The answer is actually simple. We should look everywhere. The data could be absolutely everywhere. Because the user wants to read data, that data that the user is reading might be recent, but maybe they are reading old data. Maybe they are reading data that was created 1 year ago, right? And maybe they are reading data that was created just 5 seconds ago. So just to give you the intuition, the data that was modified 1 year ago is probably long flushed to HDFS because it's very old, so maybe that's very old data here. And the very fresh data that was just created 5 seconds ago might be here. And maybe here we have data created 1 hour ago. So the answer is everywhere. We need to look everywhere. It could be everywhere. Who agrees with that? Right? So we look everywhere. And maybe I'll find a few, depending on what the user wants to access, a few here, a few here, a few here. And then I give everything to the user. If there's multiple versions of the same, I can just eliminate the older versions and just take the latest versions. But I anyway need to look everywhere. Okay? So with that everywhere, I will now let you have a break of 15 minutes, and then I'll take it from there. And feel free to ask all the questions you want. I'm really taking the time to go through the questions. So see you in 15 minutes. Thank you.